Welcome to our deep dive into Nvidia's latest performance benchmarks for the cuFFTMp library. Released today, these results demonstrate significant computational advances across Nvidia's newest GPU architectures, with the multi-node fast Fourier transform library achieving approximately 2x speedup on H100 systems compared to previous generation A100 hardware. At 2048 GPUs, performance reaches an impressive 1.69 petaflops per second. Today, we'll explore how these improvements scale across both Hopper and Blackwell platforms and what they mean for scientific computing applications. Let's start with the Hopper architecture results. Testing on the EOS supercomputer, built with DGX H100 systems, revealed consistent 2x performance improvements across all GPU counts when comparing Hopper to the previous Ampere generation. This chart shows the scaling, from 64 GPUs at 1.8x speedup all the way to 2048 GPUs achieving 2.58x speedup. The maximum performance reaches 1.69 petaflops per second at the largest scale. What's particularly noteworthy is the consistency of improvement. This isn't just peak performance, but robust scaling across the entire range. Now let's examine the real story, Nvidia's newest Blackwell architecture. The GB200 NVL72 system, featuring multi-node NVLink technology, achieves approximately 3.1x speedup compared to Ampere systems and 1.7x improvement over Hopper for smaller GPU counts. Perhaps most impressively, the rack-scale GB200 NVL72 configuration maintains linear scaling up to 64 GPUs by keeping all processing units within a single NVLink domain. The breakthrough here is architectural. 64 Blackwell GPUs deliver execution times that even 1024 H100 GPUs cannot match. This performance breakthrough stems from Nvidia's multi-node NVLink technology. Traditional multi-node systems face increasing communication overhead as GPU counts grow, but multi-node NVLink maintains low latency communication across the entire 64 GPU domain. This chart compares communication latencies. PCIe 5.0 at 100 units, InfiniBand at 75, traditional NVLink 3 at 25, and multi-node NVLink at just 10 units. For communication-intensive workloads like fast Fourier transforms, this reduction in overhead enables the dramatic scaling we're seeing with cuFFTMp on Blackwell systems. These performance improvements translate to tangible benefits for scientific computing. The molecular dynamics simulation package, GROMACS, achieves nearly 200 nanoseconds per day on Grace Blackwell systems running the BenchPep-H test case. This represents approximately 2x faster performance than Hopper systems and over 3x improvement compared to Ampere-based configurations. For researchers, this means either completing simulations in 1/3 the time or simulating 3 times larger molecular systems in the same timeframe, a transformative acceleration for biomolecular research. The cuFFTMp library itself extends Nvidia's cuFF to support distributed multi-GPU and multi-node fast Fourier transforms. Key features include multi-node support with optimized communication, Python integration through NVMath Python, inclusion in the Nvidia HPC SDK, specific optimizations for each architecture, and support for 1D, 2D, and 3D transforms with complex data types. The addition of Python integration is particularly significant. It lowers the barrier to entry for researchers and data scientists who need large-scale FFT capabilities without extensive C++ or CUDA experience. This architectural comparison shows the generational performance progression. Ampere to Hopper delivers 2x speedup through architectural improvements. Hopper to Blackwell provides up to 1.7x speedup through multi-node NVLink, and Ampere to Blackwell achieves approximately 3.1x overall speedup. The scaling breakthrough, 64 Blackwell GPUs outperforming 1024 Hopper GPUs, demonstrates that interconnect technology is becoming as important as raw computational performance for scaling scientific workloads. As simulations grow larger, communication efficiency will increasingly determine achievable scale and time to solution. In conclusion, Nvidia's cuFFTMp library demonstrates significant performance gains across successive GPU architectures, with the Blackwell platform delivering breakthrough scaling through multi-node NVLink. For scientific applications, this translates to 2 to 3x acceleration for workloads like molecular dynamics. The library is available now as part of the Nvidia HPC SDK with Python bindings through NVMath Python. Complete benchmarks are available on the Nvidia developer blog. As we move forward, these advancements highlight that communication efficiency is now as critical as computation for scaling scientific discovery to new frontiers. Thank you. Today's benchmarks reveal more than just performance numbers. They demonstrate a fundamental shift in how we approach large-scale scientific computing. With interconnect technology enabling unprecedented scaling, researchers can tackle problems previously considered intractable. Nvidia's cuFFTMp library, optimized across Ampere, Hopper, and now Blackwell architectures, provides the tools to transform this potential into discovery. As we continue to push the boundaries of what's computationally possible, it's clear that both raw compute power and intelligent communication architecture will define the future of scientific simulation.